In a single-phase system, there is only one voltage waveform flowing through the circuit. In a three-phase system, there are three separate voltage waveforms that are out of phase with each other. In a three-phase system, the voltage between any two phases is equal to the phase voltage. However, the voltage between any phase and the neutral conductor is equal to the line voltage. The line voltage in a three-phase system is approximately 1.73 times the phase voltage. For example, in a 208/120 volt system, the phase voltage is 120 volts and the line voltage is 208 volts. In single-phase systems, power is calculated as power equals voltage times current times power factor, where power is in watts, voltage is in volts, current is in amps, and power factor is usually 1 for resistive loads. In three-phase systems, power is calculated differently depending on the type of load. For unbalanced loads, power on each phase is calculated using the same formula as for single-phase systems, and the total power is the sum of the power on each phase. For balanced loads, power is calculated using the formula power equals 1.73 times voltage times current times power factor. Let's work through an example for a 10 kilowatt water heater connected to a 208 volts three-phase system. Using the unbalanced load method, power on each phase is 5,000 watts, assuming the load is evenly split. Total power equals 5,000 watts plus 5,000 watts, which equals 10 kilowatts. Using the balanced load method and assuming a power factor of 1, power equals 1.73 times 208 volts times 23.14 amps times 1, which equals 8,655 watts. The power calculation methods yield different results because unbalanced loads create phase imbalances. In this example, the unbalanced load method results in 10 kilowatts of power, while the balanced load method results in 8,655 watts. For service calculations, it is typically more accurate to use the unbalanced load method. However, for power balancing and transformer sizing, it is acceptable to use the balanced load method for three-phase loads. To elaborate further, let's consider the differences and applications of these methods in more detail. Firstly, the single-phase power calculation, power equals voltage times current times power factor, is straightforward and applies to typical residential circuits and single-phase equipment. The power factor accounts for any phase difference between voltage and current, with a value of 1 indicating a purely resistive load, where voltage and current are in phase. Secondly, when dealing with three-phase systems and unbalanced loads, it's crucial to calculate the power on each phase separately and then sum them to find the total power. An unbalanced load occurs when the loads on each phase are not equal, which is a common scenario in many electrical systems. This method provides a more accurate representation of the actual power consumption in each phase. Thirdly, the balanced load method, power equals 1.73 times voltage times current times power factor, is used when the loads are evenly distributed across the three phases. This simplifies the calculation and provides a good approximation for situations where the phase loads are nearly equal. In practice, perfectly balanced loads are rare, but this method is useful for estimating total power consumption for equipment like three-phase motors or heating elements where the load is designed to be evenly distributed. It's essential to understand the implications of using each method. The unbalanced load method is preferred for service calculations because it considers the actual load distribution on each phase, which can impact the overall service capacity and conductor sizing. On the other hand, the balanced load method simplifies calculations for panel balancing and transformer sizing. When balancing a panel, the goal is to distribute the loads as evenly as possible across the phases to minimize neutral current and voltage imbalances. Transformer sizing involves determining the appropriate transformer capacity based on the expected load, and the balanced load method can provide a reasonable estimate for this purpose. Now let's address some practical considerations. In real-world applications, loads are often a mix of single-phase and three-phase equipment, and the system may not be perfectly balanced. Therefore, it's essential to carefully analyze the load distribution and apply the appropriate calculation methods. When in doubt, it's generally safer to use the unbalanced load method for service calculations to ensure that the electrical system is adequately sized. Furthermore, it's important to consider the power factor of the loads. Most electrical equipment has a power factor less than 1, which means that the apparent power is greater than the real power. This difference is due to reactive components in the load, such as inductors and capacitors. Power factor correction can improve the efficiency of the electrical system by reducing the current required to deliver the same amount of real power. In summary, understanding the different power calculation methods for single-phase and three-phase systems is essential for electrical professionals. The unbalanced load method is more accurate for service calculations, while the balanced load method simplifies panel balancing and transformer sizing. Always consider the load distribution and power factor to ensure accurate power calculations and efficient system operation. Now, let's delve a bit deeper into the specific context of a 208/120 volts three-phase system, as this is a common configuration in commercial buildings. In this system, the 208 volts is the line-to-line voltage, which is the voltage measured between any two phases. The 120 volts is the line-to-neutral voltage, which is the voltage measured between any phase and the neutral conductor. This configuration allows for both 208 volts three-phase loads and 120 volts single-phase loads to be served from the same system. When calculating the current for a 208 volts three-phase load using the balanced load method, you use the formula current equals power divided by 1.73 times voltage times power factor. If we have a 10 kilowatt balanced three-phase load with a power factor of 1, the current would be 10,000 watts divided by 1.73 times 208 volts times 1, which equals approximately 27.75 amps. This is the current that would flow through each phase conductor. When calculating the current for a 120 volt single-phase load, you use the formula current equals power divided by voltage times power factor. If we have a 1.2 kilowatt single-phase load with a power factor of 1, the current would be 1200 watts divided by 120 volts times 1, which equals 10 amps. This is the current that would flow through the phase conductor and the neutral conductor. It's important to balance the single-phase loads as much as possible across the three phases to minimize the neutral current. If the loads are perfectly balanced, the neutral current will be 0. However, in reality, there will always be some imbalance, and the neutral conductor must be sized to carry the expected neutral current. In addition to calculating the current for individual loads, it's also important to calculate the total load on each phase of the system. This is done by summing the currents for all the loads connected to each phase. Once the total load on each phase is known, the service conductors can be sized to carry the maximum phase current. The National Electrical Code, or NEC, provides guidelines for sizing service conductors and overcurrent protection devices based on the calculated load. Another important consideration is voltage drop. Voltage drop occurs when the voltage at the end of a circuit is less than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To minimize voltage drop, conductors should be sized large enough to carry the current without excessive voltage drop. Finally, it's important to properly ground and bond the electrical system to ensure safety. Grounding provides a path for fault current to flow back to the source, which allows the overcurrent protection devices to trip and energize the circuit. Bonding ensures that all metal parts of the electrical system are at the same potential, which reduces the risk of electric shock. The NEC provides detailed requirements for grounding and bonding electrical systems. In summary, when working with 208/120 volts three-phase systems, it's important to understand the voltage relationships, power calculation methods, load balancing, conductor sizing, voltage drop, and grounding and bonding requirements. By following the NEC guidelines and using sound engineering practices, you can ensure a safe and reliable electrical system. Let's now explore the practical implications of choosing between the balanced and unbalanced load methods for different applications. When dealing with service entrance calculations, it's generally more conservative and accurate to use the unbalanced load method. This is because service entrance conductors and equipment must be sized to handle the maximum possible load that could be drawn at any given time. By calculating the load on each phase separately and summing them, you account for any potential imbalances that may occur. This ensures that the service entrance is adequately sized to handle the maximum load, even if the loads are not perfectly balanced. However, for panel board sizing and transformer sizing, the balanced load method can be a reasonable approximation, especially when dealing with loads that are expected to be relatively balanced. Panel boards and transformers are typically designed to handle a certain amount of load on each phase, and if the loads are reasonably balanced, the balanced load method can provide a good estimate of the total load. However, it's important to consider the potential for future load growth and to size the panel board and transformer accordingly. In addition to the balanced and unbalanced load methods, there are other factors that can affect the accuracy of power calculations. These factors include the diversity factor, the demand factor, and the load factor. The diversity factor is the ratio of the sum of the individual maximum demands of the loads to the maximum demand of the entire system. It accounts for the fact that not all loads will be operating at their maximum demand at the same time. The demand factor is the ratio of the maximum demand of the system to the total connected load. It accounts for the fact that the system will not be operating at its full capacity at all times. The load factor is the ratio of the average load to the peak load over a period of time. It indicates how efficiently the system is being utilized. By considering these factors, you can refine your power calculations and obtain a more accurate estimate of the actual load in the electrical system. Another important consideration is the type of load being served. Different types of loads have different characteristics that can affect the power calculations. For example, motor loads typically have a high inrush current when they start, which can significantly increase the demand in the electrical system. Lighting loads can have a harmonic content that can distort the voltage waveform and increase the current. Electronic loads can have a high crest factor, which is the ratio of the peak current to the RMS current. By understanding the characteristics of the different types of loads, you can more accurately predict their impact on the electrical system. In addition to the NEC, there are other standards and guidelines that can be helpful in designing and analyzing electrical systems. These include the IEE standards, the NC standards, and the UL standards. The IEE standards provide guidance on a wide range of electrical engineering topics, including power system analysis, protection, and control. The NC standards provide guidelines on various aspects of electrical equipment and systems, including safety, performance, and testing. The UL standards provide requirements for the safety of electrical product. By following these standards and guidelines, you can ensure that your electrical system is designed and installed in accordance with industry best practices. In conclusion, accurate power calculations are essential for designing and analyzing electrical systems. The balanced and unbalanced load methods provide different approaches to calculating power, and it's important to understand the strengths and limitations of each method. By considering the diversity factor, the demand factor, the load factor, and the type of load being served, you can refine your power calculations and obtain a more accurate estimate of the actual load in the electrical system. By following the NEC and other relevant standards and guidelines, you can ensure that your electrical system is designed and installed in accordance with industry best practices.